if you go over time, I'm going to take it out of your questions.
Okay.
We will be showing.
All right.
We will be showing warnings for the time. We will show a 10-minute, 5-minute, and 1-minute warning.
Okay. Now, usually I'm in the right. I mean, I tried once and it should work. Maybe 1 minute more, but let's see.
So normally the warnings will remain there a few seconds. If you acknowledge them, they will remove them faster if they are annoying you. So I hope they are not too troublesome.
Yeah, it is not automatic.
Should we start?
It is not automatic. It is done by hand.
I see.
Yeah. So, Steve, please watch that they come on time, but I'm sure they will. They are doing very good.
Okay, so let's start the session. I'm Stephen Park from Fermiland, the home of the neutrino, pretty much. Anyway, so our first speaker is Francesca Dori, from CEA, who's going to tell us about neutrino coherent scattering.
Yes, thanks a lot. Yes, so I will so first of all, thanks a lot for the invitation. It's really a wonderful workshop. So and I'm really happy that I'm here and I have the opportunity to talk about coherent elastic neutrino nuclear scattering. So I will give you a bit the experimental status and theoretical prospects. First of all, just to be all on the same page, let's clarify what I mean with the sevens. So you will see this acronym a lot in the presentation. So 7 stands exactly for coherent elastic neutrino nuclear scattering, and it is an interaction in which a neutrino scatter off a nucleus via the exchange of a Z boson, and the nucleus recoil as a whole. As you can see from this paper here, it was predicted a long time ago by Friedman in 1974. And what I find nice is that if you read the paper at some point, Friedman says that his suggestion may be an act of hubris, saying that this process would have been really difficult to be observed. And indeed, it took more than 40 years to finally measure the nuclear recoils originating from this neutrino interaction. So focusing a bit on the energy regime we are talking about, basically what you see here are the different interactions that a neutrino can undertake for different neutrino energies. And you see that in the high energy regime, we have interaction like deep inelastic scattering that are really disruptive for the nucleus, while here we are talking about exactly the opposite regime, in which basically we have the gentlest, if you want, neutrino interaction, where the nucleus is left as it is and it just recoils a tiny bit. And in order to have this coherence, then all the nucleon wave functions in the target nucleus must be in phase with each other, a low momentum transfer. And this means that then what we can do from also a mathematical point of view, if you want, is to calculate the cross-section by summing all the amplitudes and taking the square of the sum of all the amplitudes. And we can do so whenever this condition holds. So basically the product of the free momentum transfer that depends on the mass of the target nucleus and on the recoil energy of it is multiplied by the nuclear radius is smaller than much smaller than 1. And this in turn means that the interaction is coherent for neutrino energies up to about 50 MeV for medium-sized nuclei. So whenever this is true, we can write the cross-section in a simplified way like this, where you see basically that we have the contribution of the nucleons, so the neutrons and the proton. However, due to the fact that the proton is multiplied by the Weinberg angle, then due to the fact that this term is small, then this term is close to 0, and basically the main contribution is coming from the neutrons. So overall, the cross-section scales as the number of neutrons to the square. So remember this dependence, because it's really a fingerprint, if you want, of sevens, and it can be tested experimentally. So why we were referring at the beginning to an act of hubris? Not because of the cross-section, because actually the cross-section is rather large for the neutrino world due to this coherence effect. You can see here in blue the cross-section for sevens in cesium and iodide, that are two targets that are used for sevens observation, compared to inverse beta decay, to neutrino electron neutrino scattering, and so on. And the cross-section is actually rather large. The problem is, however, due to the coherence condition, we have really tiny recoil energies, and in particular the maximum recoil energy, that can be written approximately in this way, for neutrino energies of about 50 MeV, is in the keV range. So again, if we want to take cesium nuclei as an example, the maximum recoil energy is about 40 keV. And the problem here is experimental, because these energies are typically below the detection threshold of the conventional large neutrino detectors that are used for many other studies. However, in the recent years, the technology developed for dark matter detection really improved and became sensitive to keV and tens of keV recoils. So we can really exploit the same technology also to observe sevens. So this is about the detector. So it's really important to have really low threshold in order to see these tiny recoils, but that's not the only thing we need to have. There are also some constraints that the source needs to follow. And first of all, we need to have an high flux source of neutrinos in order to have as much statistics as possible. It has to be well understood, so the flux must be known with very good precision in order to know how many neutrinos are interacting in our detector, and ideally it should be pulsed, which means that we can operate a tiny time window whenever we expect the pulse of neutrinos, and enclose it right after in order to accumulate as less background as possible. And finally, ideally, we should have multiple flavors of neutrinos, since sevens is an interaction that is basically independent, if you want, on the flavor of the neutrino. So if you have multiple flavors and ways to distinguish among them, then you can study different properties. There are two types of neutrino sources that we can consider that follow more or less these requirements. And one is a spallation neutron source, so to put the detector close to it, where the neutrinos are produced from the decay of pions and the subsequent decay of muon, or at nuclear reactors, where the neutrinos and actually the antineutrinos are produced in beta decays of fission fragments. So we will see experiments using both technologies, but let's start with the coherent experiment. That is the first one that observes indeed sevens process that operates close by a spallation neutron source, where we have a flux of proton that hit liquid mercury target, and then, as you can see here, pions are produced. The pions decays order of nanosecond into muons and muonic neutrinos, so this is our prompt signal. And then the muon neutrinos, the muon in order of microsecond decays instead in electrons, electron neutrinos, and muon antineutrinos. So we have also a delayed signal, and you can see here the time distribution of these two quantities. And this difference between the two is really nice, because it gives us an handle to separate the different neutrino species. Moreover, the flux is pulsed, so as I said before, it's great for reducing the background. Another great feature of Coherent is that it is a multi-target program, in the sense that, as I was stressing at the beginning, the cross-section of sevens as this peculiar and square dependence. So you want to use, in principle, as many targets as possible in order to really test this dependence. And indeed, so far we have data on using cesium iodine target and using liquid argon, but more targets are foreseen for the future. So this is, if I'm pretty sure all of you know, but in case someone missed it, this is the first observation of a seventh event back in 2017, and sevens were detected using a 15 kilos cesium iodine scintillating crystal, and about 134 events were reconstructed. You see here the distribution of the events as a function of the number of photoelectrons, so basically the energy, as a function of the arrival time for beam on and beam off. And here you see the comparison of the experimental number with the standard model prediction, so slightly below, but still compatible within 1 sigma. That's not all, because actually Coherent continued to take data with the cesium iodine data set and increase the statistics, doubling it, and it took data up to the 10th of June 2019, when the detector was decommissioned, and luckily they saw again 7 events, so they confirmed it, and as I said, doubling the statistics, so they seem something like 300 events now. And here you see the 7th cross-section that was possible to be calculated from this number, and now it compared with the standard model prediction. And again, here you can see it from a graphical point of view. So again, below with respect to the standard model prediction, but still compatible at 1 sigma level. And the main difference with respect to the 2017 analysis was in particular a reanalysis of all the systematic contributions, and in particular that of the quenching, so-called quenching factor. So the quenching factor gives you the ratio between the energy in electron recoils and nuclear recoils, and it's a term that you need to know in order to assess to know the neutrino, the energy of your nuclear recoil. And this was back in 2017, the largest systematic by far, about 25%, and it has been reduced to 3.6%, if I remember correctly, 4% more or less in 2020. So now the largest systematic uncertainty is coming from the knowledge of the flux of neutrinos. As I said at the beginning, Coherent is taking data also with other targets, and in 2020 also showed the first result using argon. So in this case, they use a 24 kilos detector filled with atmospheric argon, and the signal is again a scintillation signal. And in this case, they performed 2 different analyses, so labeled analysis A and analysis B, that differ mainly for the selection procedure, and they found compatible results, and again observed 7s with a significance of about 3 sigma. And having multiple targets, it allowed the Coherent collaboration to start to test the n-square dependence of the cross-section. So here you see the standard model prediction, and how the cesium and argon point nicely fit this prediction. The data taking is continuing concerning argon, and as far as I understood from the latest collaboration announcement, in principle 5 sigma significance should be reached with the data up to the end of 2020. So we are really looking forward for new results using argon. Since when Coherent showed that it's feasible to measure 7s, there has been an increasing attention both from an experimental point of view and a theoretical point of view that resulted in many experiments that have been proposed, and some ongoing all around the world. Among them, so if you're curious about nucleus, I've seen that there is a talk right after mine, so for sure we will know more here. So here I wanted just to mention Conus, that is maybe the other experiment in the most advanced status, that differently from Coherent is close to a nuclear power plant. So in this case, it has the advantage of having a large flux. However, the energy of the neutrinos is smaller, so this in turn implies even tinier coils. And so the detector has to have really a low threshold in order to see the events. And moreover, the flux is not pulse as for Coherent, so there is more background, but at least there are a reactor of periods that allow to study the surrounding background. So here you see a sketch, actually a picture of the detector. So it consists of 4 germanium crystals of 1 kilo each, put inside a multi-layer shield. And here you see the results that consist in the best limit on sevens by reactor antineutrinos, and the result is expressed as a function of this quenching parameter, since it depends on it. Oops, sorry. And by comparing basically their findings, so their best limit with the theory prediction, they're able to put some limits as well on this quenching parameter given their data. So that's already fantastic. So already the fact that after so many years we are able to see sevens, to measure this process, to learn if it is a standard model-like or not, it's already a lot. But actually, in the last years, there were many more ideas that came up and of interesting physics that can be done with sevens. And to better understand which kind of physics we can do, we can just have a look again at the cross-section. So this is the cross-section as a function of the nuclear recoil energy. And in the end, it depends on the standard model neutrino, vector, proton, and vector neutron couplings. And of course, in case of, in case of new interactions, of new neutrino interaction, then we have that these couplings may be modified. So new fitting for these couplings in a possible extension gives light about new interaction. If you have new neutrino properties, these will appear as additional terms in this cross section. So you may look for them. There is the dependence on the Weinberg angle, so we can do electroweak precision test. And finally, there is the dependence on the distribution of the nucleons, so the proton form factor and the neutron form factor. And in particular, the neutron form factor, given that, as I said before, this term is small, so the proton contribution is very much suppressed. So we can really infer a lot of information on the neutron form factor. And that's great because actually the proton one is very well known. So we know the charge distribution of the protons inside the nucleus thanks to electron scattering, muon spectroscopy. So it's a quantity that is very well known for all the nuclei, while the same is not true, is not valid for the neutron distribution. And by measuring the form factor, we can infer information on the so-called neutron distribution radius. And there are so I put here some references that came to my mind, but there are even more about papers that studies this topic. What I wanted to show here is a recent work in which we studied both the coherent cesium iodine dataset and atomic parity violation in cesium that measure the weak charge of cesium. And since they both depend on the radius of cesium, of the neutron distribution in cesium, it allowed to, for the first time, to disentangle the contribution of cesium and iodine that are the targets used by coherent, and to constrain for the first time the two neutron skins separately, where the neutron skin is the difference between the neutron radius distribution and the proton one. A similar analysis can be also done with argon using coherent-only data, and basically, unfortunately, in this case, the statistics is such that only upper limits can be put, and you see here the two different analyses that are in rather good agreement. So here, more statistics will be needed in order to really say something on the possible predictions and for the neutron distribution radius. However, what I wanted, I want to add before to close this chapter about nuclear physics is that these measurements of Rn are important not only for nuclear physics, obviously it's a fundamental parameter that is unknown for many nucleus, but it's also very important for its link with the astrophysical sector. Indeed, the radius of the neutron distribution is very much correlated with the equation of states of neutron-rich matter, like for instance neutron stars. So information of the neutron distribution radius can help us to better constrain the equation of state. So now let's move to another sector, namely Electroweak precision test. So as I was saying before, Coherent allows us to measure the Weinberg angle, and here you see the newest Coherent result using the latest CSI dataset. However, the measurement, I mean, the uncertainty on this measurement is not competitive, given the fact that, as I said, neutrinos couples mainly to neutrons, so the proton contribution is suppressed. However, sevens is still helpful because, again, if we combine Coherent with atomic parity violation, since they both depend on the neutron distribution radius and on the Weinberg angle, we can fit for both these quantities at the same time and extract information on both of them, including their correlation. And here you can see more in, graphically displays the result, so the combined fit of atomic parity violation plus coherence, and how it compares to the other fits of the Weinberg angle at different momentum transfer. And basically, this is a reevaluation of the old APV value. And if you wonder why the uncertainty increased, despite the fact that we are even adding the coherent data set, is that in this case, the value of the neutron distribution radius was extrapolated from hadronic experiments using antiprotonic atoms, okay? And this is known to be affected by considerable model dependencies. So basically, while in this case we take everything from data, so it's completely data driven, and that's why the uncertainty increased a bit. Another sector that we can test is that of non-standard interaction and possible new mediators that can modify the cross-section of sevens. So here you find again the usual cross-section I'm showing you in several slides, and how this non-standard interaction may modify the couplings of neutrinos to protons and neutrons. So they appear as these additional terms where these couplings basically parameterize the size of non-standard interaction relative to the standard model one. And this is another way to write these couplings as a function of the momentum transfer and the mass of the mediator. And basically we have two scenarios here. One in which the momentum transfer is much smaller with respect to the mass of the mediator, so the coupling becomes basically constant, and we can fit directly for the coupling using an effective approach. Or the case where we have a light mediator, so the opposite relation holds, and the couplings becomes momentum transfer dependent. And in this case, one can make assumption on the possible new physics. So, for instance, thinking about a new gauge symmetry with an additional vector mediator like a Z prime, or a scalar mediator like a phi boson, and fit for the parameters of these new mediators. So here you see some results that have been obtained recently using the Coherent dataset, both CSI and argon, for different light mediators models, so-called B-L and mu-L allow and the universal one. And what is nice here is that Coherent not only allows to put limits above 5 MeV, but actually the best limits below are coming from Conus, that is another experiment using 7. So it's really 7s dominated. So if you want a study where there are also even more models and complementarity with the same limits coming from the neutrino oscillation data, I will look here. While here you can find also some limits in case of scalar mediators. And that's instead for heavy mediators. So as I said before, we can directly fit for the couplings. There are many of them. So fitting for all of them when they are all allowed to be different from 0 is really computational challenging, but some works like this one and this one here did it. However, in most of the cases, what we've done is also to take just a couple of them different from 0 to make more, to put more meaningful constraints. And that's the case, for instance, in these two plots that I reported here, where you can also see how they compare with the similar limits coming with the oscillation analysis. So finally, another important sector in which we can learn a lot is about new possible neutrino properties. In fact, in the standard model, we know that the neutrino electric charge is of course 0, and there are no electromagnetic interactions at the level. However, such interaction can arise from loop diagrams at higher orders. So if we consider a kind of interaction like this and an effective Hamiltonian like this, then just by focusing on the vertex function, we can see basically all the Lorentz invariant form factors that at free momentum equal to 0 are equal to the charge on a pole and magnetic and electric dipole moments. And in the standard model, what you find is that only this term survive, and even in the standard model, you have some correction arising from higher loops that is related to the so-called neutrino charge radius. So this term here that is precisely predicted in the standard model and depends on the flavor of the neutrinos. So here you find some nice constraints that was possible to put on neutrino charge radii, millicharges, and magnetic moments thanks to Coherent, and in particular, Coherent allows to put the only existing laboratory bound for muonic neutrinos. So actually, that's not even all. So there is much more that you can do with 7s, but I didn't have time. So I just put here the references for if you are more interested in connection with the dark matter sector, for the axion searches, the supernova neutrinos, and the sterile neutrinos. So you may find some interesting works here and in the reference therein. So to conclude, I hope that even if maybe it was a bit fast and a lot of information, at least I gave you the feeling that 7s has really opened a fantastic window to a plethora of physics observables. So many of them that is not possible to accommodate all of them in a talk. And from an experimental point of view, it's an exciting moment because new results should come and are expected soon. And from the theory community, there is a large and growing interest with application to many different areas and complementarity between different sectors. Thank you.
Thank you. Very nice talk, Francesca. This talk is open for questions. I have a question. Could you go back to your slide where you show the figure of the cross section versus the number of neutrinos, the number of neutrons?
Neutrons, yes.
Yeah.
Yeah.
So the theory includes, a quenching factor. If you were to plot this as a log-log, how close to a straight line is it?
So you mean, of course, in the theories there is some information on the quenching factor. Here, actually, the different lines are for different form factors that you can assume for for the proton and the neutron form factor, and here is a form factor equal to unity, that is full coherence, while this is another form factor. Of course, also the quenching has an impact, and this is shown. I think it's included in the uncertainty that is shown here.
Okay, so let me just understand. The black line, if I was to plot this on a log would be a straight line. Is that correct?
Exactly.
Okay, all right. Okay, very good. Thank you. Any other questions?
I have one. Sorry, I cannot raise my hand because I am host and the option disappears.
Okay.
I think it was the next slide to this one. But yes, so you have all these options around the world. I noticed. So how important is that the pulsing of the beam to reduce the atmospheric, well, the cosmic background? Because, for instance, the European spallation source, I think it's really intense, but if I believe it's not pulsed. So I don't know.
No, exactly, it's not pulse, but I mean, it is important. I mean, at least it makes your life easier for sure, because you can open a tiny time window just before your data set and right after, and you have a continuous subtraction of your background, but is not fundamental. I mean, this is also shown by Conus if you want. So Conus doesn't have a pulsed beam, and it's able already to control the background and put some limits. Of course, in this case, you gain a lot if you increase the statistics. So for instance, the European spallation source will have this great advantage. So your signal will be even more, and so should stand up even more with respect to the background.
Thank you.
Pilar? This is the last question, then we must move on.
Yes, hi. Sorry, if I just may make a comment on this last comment by Enrique. So at the European spallation source, the beam is pulsed, but very long pulse.
Mm-hmm.
So you can still, so the main difficulty that this brings into the problem is not actually for background rejection, but more for distinguishing between the prompt and delayed signals. So a cool thing that happens for the coherent experiment is that because you have these very short pulses, you can actually distinguish between the neutrinos that come from the muon decay and from the pion decay. And at the ESS, this is not possible. So actually you have this mixture between different flavors. This is the most relevant thing, but yeah, so that was just a comment.
Yeah, thank you, Pilar. Yes, indeed, it's not pulse in the sense that it's rather long, yeah.
And thank you, by the way, Francesca. That was a very nice talk.
Yeah,
Okay,
thank you.
Let's thank Francesca once more.
Thank you.
And we will go on to the PhD forum. And I believe our first speaker is Beatrice Mori, who is going to also talk about sevens, and she really is from CEA.
Hi. Okay, I'm going to show my screen. Okay. So first of all, thank you for this opportunity. I'm going to present you the alternative prototype we are realizing in CEA for the nucleus experiment. So nucleus experiment is interested in the coherent.
I'm sorry for interrupting, but there must be something with the microphone. Maybe it's a little bit, you're a little bit far from the microphone.
Now is better?
Better the volume, but it's sound behind it.
Let me see, maybe. Is it better now?
A bit noisy.
Can you hear me?
Maybe try to turn off the sound of the others and only your speak or something. Now there is no noise. Maybe we can switch her. Huh?
Go on, Belen. I just muted there. It could not be possible.
No, maybe Beatrice, maybe if we switch you to after some next student, you can try with another computer or something. Otherwise, we have your PDF, slide PDF, and we could pass them. But no, if you talk, it's the same problem. So, okay.
So
Try to
look, enable a breakout room, and I can try with Beatrice in the breakout room to see if we can fix the problem.
I cannot do that. That's not possible to open a breakout room now.
Okay.
Okay. Beatrice,
Well,
Can you hear me now?
with noise. Do you have another computer?
I will, Beatrice, I will send you a link to a different Zoom meeting, and then we can try to see if we can fix it meanwhile.
Steve, we don't hear you.
I muted. Sorry. Let's move on to the next speaker, and you can try and resolve that issue.
Offline.
And we'll put you back at the end, Beatrice. Okay, so the next speaker is Valentina Domi, who's going to talk about neutrinoless double beta decay, and she's from Gran Sasso.
Yes, hi, can you hear me?
Yes, perfect.
Yes.
Just a second, let me switch on my video. Maybe now you can also see me, if everything is working properly. And also I have shared my screen. Can you see my slides?
Yes.
Yes, we can.
Okay, fantastic. Okay, so first of all, again, thanks for this opportunity. And today I would like to summarize you part of my PhD work on the research for neutrinoless double beta decay of tellurium-128 with the Coherent experiment. If I can move on, okay. The double beta decay is a rare second-order Fermi-weak nuclear transition, and that is visible on into even nuclei when the single beta decay is energetically forbidden. In this transition, two neutrons are simultaneously transformed into two protons, and in the final states, there are two electrons, and depending on the decay mode, we can have a couple of antineutrino or not. In case of the two neutrino double beta decay, the electrons are emitted together with the neutrinos, while in the neutrinoless double beta decay, only the electrons are present in the final states. And this is the interesting process to be searched for, since this is a beyond the standard model process, and its observation would demonstrate that the lepton number is not a symmetry of nature, that the neutrinos have a Majorana component, and it would also open the way to a possible explanation of the matter-antimatter asymmetry of the universe. In Coherent, we search for this decay in tellurium-130, and we do it with a tone-scale array of 988 tellurium dioxide crystals, so that we operate as thermodetectors at the cryogenic temperature of 10 millikelvin. Coherent is located at the Gran Sasso National Laboratories, and it is characterized by a ultra-low background level and an excellent energy resolution. Thanks to these characteristics, Coherent is also able to search for other rare processes, such as the neutrinoless double beta decay of tellurium-128, which is another double beta decay emitter, tellurium isotope, that is characterized by a high natural isotopic abundance that is almost 32%. However, this transition is located in a high populated region of the energy spectrum. And for this reason, past experiments that used tens of kilograms of tellurium dioxide had a poor sensitivity to this decay. And the latest limit from direct experiment is set to 1.1 10 to the 23 years. and most stringent limits come from the geochemical experiments, which, however, cannot distinguish between the two decay modes. So this measurement of 2 10 to the 24 years definitely refers to the sum of the two decay. And Cuore, with its ton scale mass, is able to reach a factor 10 higher sensitivity to this decay, and these results might be also competitive with the geochemical results. So this is the statistical approach that I am adopting for this research, that is a Bayesian fit, Binet fit based on the BAT software, where the parameter of interest is the double beta decay signal rate. The full containment efficiency for this process was evaluated by a Monte Carlo simulation, and it turned out to be almost 98%. And these are the background structures that I have to include in my fit model, which are a gamma line from thallium 208 and a gamma line from manganese 54. I validated my analysis on toy Monte Carlo simulations. Yes, and from which I extracted informations in like these parameters here that I used to do my simulations. And thanks to this, I could extract the limit setting sensitivity test for Cuore, which is defined as the median of the distribution of the 90% credibility interval limits on the half-life. To do this, I performed 10 to the 4 Monte Carlo simulations that I, only with the background components that I fitted with the signal plus background model. And from these fits, I extracted the 90% credibility interval half-life limits, and I constructed this distribution. And from this median, you can see that the limit setting sensitivity test for Cuore to the neutrino's double beta decay of tellurium-128 is 2.2 10 to the 24 years, and that Cuore can then improve by more than 10 times the limit of this decay, and it can possibly overcome the geochemical results. And with this, I concluded.
Right. Thank you very much. We have time for one question. So can you can you convert this number to delta M squared or M beta beta?
Yes, I
mean,
can.
you need to know the nuclear cross section, but I'm not used to these units very much.
Yes, it is possible to do this in the neutrino, the light Majorana neutrino mass mechanism. It is possible to convert this number to M beta beta, and for this is necessary to have the nuclear matrix elements, and this corresponds to, I did it, this corresponds roughly to the order of the electron volt, and this is a limit that is much less stringent actually than with respect to other research with this isotope. So the conversion of this decay in M beta beta does not actually give an important information regarding the M beta beta mass.
All right, thank you very much. All right, thank you, Valentina, for a nice talk. And we need now to move on to the next talk, which is by Kenny Vetter, who is also going to talk about Cuore, and he's from Berkeley.
Great, thanks very much. Can you see my slides and can you hear me?
Yes.
Fantastic. So yes, as Valentina very eloquently spoke about Cuore and some of our science goals, today I'll speak about some of the active noise cancellation algorithms that I've been working on to improve the quality of our data. So even though this is intended for Cuore, all of the research and development that we've done for this project so far has been local at UC Berkeley. So we have an Oxford dilution refrigerator where we test our NTD calorimeters and transition edge sensor-based light detectors. And we cool these down to about 12 millikelvin. Now, we see a lot of noise in our detectors, and I'll show some plots that demonstrate that. So in order to monitor this noise, we put accelerometers on the 300K plate, which you can see on the top right. And we also add a Helmholtz coil, which can measure the electrical noise in the environment, and we attach that to our DAQ board. And our goal is to remove the vibrational and the electrical noises from our devices using these, or from our detectors using what I'll call these auxiliary devices, the accelerometers and the Helmholtz coil. So to approach the problem, there are two different methods that I'll describe. There's what I call a linear noise cancellation, which basically does everything in Fourier space. And then there's also this adaptive noise cancellation technique, which looks at a discrete Laplace transform, also known as the Z transform. And in both of these cases, we're basically going to try to find a transfer function from one device to the other, ideally from, from auxiliary to bolometer. So the nature of noise prediction goes something like this. You have some other diagnostic device like our accelerometer or our Helmholtz coil. In this case, this is just the Helmholtz coil. And it's got some time stream, and you assume that there's going to be some linear transfer function from one to the other, and you look at a series, an ensemble of noise events, and you construct the average transfer function. And there are some other manipulations that you can do that I get into my poster to kind of refine this. But ultimately, the goal is to produce a predicted noise signal, which I've shown here in red. And you can see that this predictive noise signal very much matches up with the electrical noise that you see in the bolometer, which is in blue. And I've tried to pick out a point in time where you can actually see them match up at certain points. So particularly between here, 845.1 and 0.2, you can see there's a strong match of the noise patterns. And then when we subtract red from blue, we get a new signal that's effectively cleaner. So we can characterize the improvement of the energy resolution using this algorithm. And I promise I'll show something that cleans this up in a minute. But you can notice that there's that we do actually make the energy resolution of our devices better. And this is not anything in hardware. This is all done in software and in post-processing. So this can be applied readily so long as you save your data. You don't need to write it in live time. If we compare the resolutions of the fits, so those 5 peaks there are 5 different LED pulses of different pulse widths, which represent gamma rays of different energies. And you can see that we have a statistically significant improvement in our resolution for each of these 5 amplitudes. And it's about 5 or 6%. Now, we can take this idea and kind of make it more mature by not just doing a statistical ensemble average, but instead we can build an adaptive noise canceling algorithm. Now, for those of you who have ever used noise canceling headphones that have a microphone on them, you might be familiar with this idea where you will actually hear the noise level drop as your device starts to adapt. So I won't go into the whole schematic here, but for those of you who are familiar with LMS error algorithms, this is essentially that, where the error function that I'm using is just the difference between the actual signal and the predicted signal. And so here are some results. Again, we've got some time stream with a bunch of LED pulses so that we can actually measure the detector resolution. And then we predict the signal again in red using this adaptive algorithm, and you can see that it does a very effective job of capturing that vibrational noise. Here, we're not using the Helmholtz coil, we're using the accelerometers to try to measure this low frequency noise. And you can see that we effectively capture the low frequency modulation of the baseline. When we then subtract red from blue, we clearly see a much cleaner signal. Now here we only have one amplitude or one width of LED pulse, so we should expect just a single pulse amplitude, and that is more or less what you see once you subtract out the noise. Of course, there is this higher frequency noise, but the low frequency noise that we would expect from vibrations is effectively removed. And while I haven't quantified these data to the same point, there are some things that I'll note. First of all, if you look at the distribution of all of the baselines from these LED events and you measure the RMS of that baseline, you see that the distribution is left shifted after the active noise cancellation, meaning that we've effectively reduced the RMS of our signal. And then one other thing that's nice to see is that while we don't actually improve the resolution, at least by eye, which we actually expect because we're in a low frequency noise canceling regime, we don't introduce any sort of bias, which is very nice to see. So we effectively can reduce some of the noise without affecting the actual energy measurement of the detector. So one would not need to say recalibrate. And thank you.
All right, thank you very much. Question? All right, if there are no questions, let's move on to our next speaker, Patrick Bolton, who is also going to talk about neutrinoless double beta decay in SUSY, and he's from the University College London.
Hi there. Hi. I'll just share my screen. Can you hear me well?
We can hear you.
Okay. Can you see my screen as well?
Yes.
Yeah. Okay. So I'm moving on to the theory side here, and I want to discuss neutrino cell beta decay with R parity violation and light neutrinos. So firstly, I just want to introduce the basics here. Supersymmetry is still sort of a well-motivated model or extension to the standard model. And we can consider sort of a minimal version of this called the MSSM. And that's where we add a supersymmetry partner to each standard model field. So we have scalar partners to the leptons and quarks. We have so-called neutralinos, which are fermionic partners to the standard model gauge bosons. We have gluinos, and we have a gravitino as well. So in general, in your theory, you can write down terms which violate lepton number and baryon number. The issue is, however, that this final term here, which is baryon number violating, induces proton decay. So there are very stringent constraints from sort of the non-observation of proton decay. So the common thing to do to sort of avoid sort of a fine tuning of this coupling is to introduce a discrete symmetry called R parity, where your standard model fields are positively charged, your SUSY fields are negatively charged, and that will forbid these terms. However, we're interested in this second term here, which is lepton number violating and can induce neutrino cell beta decay. So I'll walk you through that now. So how does this work? So this is the sort of Feynman diagram for neutrino cell beta decay. We have this lambda prime at each vertex, and we can either have the exchange of a neutralino or a gluino. And what is commonly assumed is that the masses of these SUSY partners are larger than the momentum exchange of neutrino cell beta decay, which is around 100 MeV. So this is a short range process. And because of this, we can use a dimension 9 term in our sort of standard model effective field theory to sort of determine the sort of predicted half-life for the process. And this will depend on these two sort of non-standard coefficients, epsilon 1 and epsilon 2, which themselves multiply these matrix elements, which encode sort of the complicated nuclear physics. Sorry. So more specifically for this neutrino process, this sort of blue blob here can be shown to be sort of this in SUSY, where you have the exchange of a lepton or an up squawk or a down squawk. And in the previous literature, you can decompose these non-standard coefficients in this way. And these are functions of all the masses that are going into these diagrams. So the mass of the neutrino and the mass of the sort of fermions as well. And what is commonly assumed from bounds on the chargino is that the sort of mass of the neutrino needs to be larger than a certain sort of cutoff. But this can actually be evaded based on the particular model, and the neutrino can actually be very, very light or even massless. And if the neutrino is then lighter than the momentum exchange, you can have a long range exchange similar to sort of a light neutrino. So to sort of describe this, we replace the sort of short range expression with an interpolating function, which is sort of equivalent to the sort of propagator of this neutrino. So what we want to do is use this sort of approach to now put bounds on this coupling lambda prime as a function of the mass of the neutralino, lightest neutralino. So we take the sort of current lower limit from one of the experiments, for example, this germanium Coda 2 experiment. And what we do is place an upper bound on lambda prime as a function of the mass of the neutrino. But the issue is this also will depend on all of the SUSY masses that are going in. And one of the most important ones is the selectron mass. So what we did is we did a scan over all of the allowed values of the SUSY partner masses based on the sort of collider constraints, and essentially plotted this constraints for the sort of lowest value of this selectron mass allowed by, say, Atlas and CMS. And this depends on also depends on the mass of the neutrino. And here we're comparing this with constraints from CKM matrix elements, this pion decay ratio, and BBN, Big Bang nucleosynthesis constraints. So finally, to conclude, or before the conclusion, I just wanted to say that this G-2 anomaly is still around. This can also be induced by the presence of a neutrino and also smuons. So these are the partners of the muons. And if we assume that these are degenerate with the selectron, we can then plot the sort of favored region from G-2 in the same parameter space as the constraint from Atlas and neutrino star beta decay. And this is showing that the sort of favored region is excluded by Atlas for small values of the neutrino mass. And then for larger values, it's constrained by neutrino star beta decay, depending on the value of this coupling lambda prime. So as this lambda prime gets smaller, this neutrino star beta decay constraint sort of goes away. So then this region does become allowed in that case. Okay, so to conclude, we've analysed this sort of R parity violating coupling lambda prime and its contribution to neutrino star beta decay. We've considered an arbitrary mass for this lightest neutrino, and to do this, we've used an interpolating function to sort of describe both the short range and long range behaviour of the process. And then what we've done is sort of constrain the parameter space using neutrino star beta decay and compare this to collider constraints and the favoured G-2 region. So I'd be happy to answer any questions you have.
Okay, thank you very much. We have time for one short question.
There's Sergei Pektov that has a question.
Go ahead.
Patrick, nice talk. Now, one question, I mean, when you add the amplitude from this R parity breaking term and the contribution from the light Majorana neutrino exchange, there must be, in principle, some interference term between the two. Somehow yes. you didn't discuss it.
No, so we're not including that currently. But of course, there would be also this contribution from a light neutrino.
And there might be some interplay between the two contributions. I mean, there could be cancellations and there could be enhancements and things like that.
There could be, yes, but we haven't sort of got to that stage yet.
Okay, thanks.
All right, thank you. Let's thank the speaker once more. Our next speaker is Stefan Sander, who's going to talk about cosmological neutrino mass bounds. And he is from IFIC.
Okay, hello, can you hear me and see my slides?
Hello, yes, we can hear you.
Okay, perfect. So hi everybody.
Slides.
You see my slides, right?
Yes.
Okay, perfect. So, well, hi everybody, and first thanks to the organizer for giving me the opportunity here to talk about my work on neutrino decay and its relation to the cosmological neutrino mass bound. This is based on the work we published last year here in Valencia together with my two PhD supervisors, Jacobo and Nuria, and Miguel Escudero, who's a former PhD student of Nuria and now postdoc in Munich. So before you get too bored of my talk, I will give you already the takeaway message, and which I want to explain in the following. So the motivation of this work was basically that, as you all know, that the cosmological mass bound in neutrinos is much stronger than the neutrino mass bound inferred from laboratory experiments. And together with our knowledge of active neutrino mass splitting, this neutrino mass bound of 0.12 electron volt is already on the limit on testing the inverted ordering scenario. And also from a model building perspective, this 0.12 electron volt is quite challenging, as many neutrino flavor models, which can successfully predict the neutrino oscillation data, have a neutrino mass with a 2-0 mass matrix with a 2-0 texture, which in generally predicts masses higher than 0.12 electron volt. So, however, you have to realize that this bound of 0.12 electron volt assumes lambda CDM with stable neutrinos. So what we did is relaxing this assumption of the stability of the neutrino, which can lead to a neutrino mass bound, which is up to 1 electron volt, and we show how this can be incorporated in concrete models. So to understand how this is possible, one needs to realize that the main constraining power of Planck and Bau comes from the neutrino contribution to dark matter, to the non-cold dark matter component today, which is given in this plot here at the right line. So in this plot, we see the normalized energy density over the course of the cosmological evolution in bold for neutrino, for two different neutrino masses of 0.5 electron volt and 0.06 electron volt. And in dashed, we see the same neutrino mass evolution of the energy density, but now with an decay rate which is faster than the age of the universe. And obviously, at late times, the energy contribution decays away, and so the main constraining power of Planck is circumvented. So now the question should be how we achieve such a neutrino decay. And obviously, we can start with a standard model, because once the neutrinos are massive, they certainly will decay. But detailed calculation of neutrino decay, of radiative neutrino decay, show that the lifetime of the neutrino will be much larger than the age of the universe. So to some extent, beyond the standard model, degrees of freedom are needed. And what we did in our work is to analyze all possible decay channels, which can be induced by two model-independent renormalizable Lagrangians, and confronting them with experimental constraints. Now, because of lack of time, I will only discuss the most promising channel, which is one active neutrino mass eigenstate decaying into one stereo neutrino, and beyond the standard model light scalar or gauge boson. Okay. From the model perspective, we started with a more or less famous U1 U minus tau model, which by itself already has a neutrino decay of the form that one active neutrino decays into another active neutrino. But we can even do more by just adding a U1X symmetry, under which a complex scalar phi and the new Fermi singlet are charged, such that the new unique Lagrangian term is of this type, and the resulting neutrino mass matrix is given here. We can assume the standard hierarchy, that the Dirac mass is much smaller than the Majorana mass, and also that the new mass scale is lower than the Dirac mass scale. So here this ensures that the CISO mechanism is at work, and we have the right properties for the stereo neutrino, which is that this is massless at tree level, and its mixing to the active states are small. Okay, analyzing this model, we end up with a decay rate, which can be parameterized like this, where we choose 0.3 electron volt for the summed active neutrino mass as a reference value, and 10 to the 14 GeV for the Maran mass. And this is the resulting plot, and the red bands show the 1 sigma and 3 sigma mass prediction of this model, given the latest new fit data on the PMNS matrix. And everything which is between this purple and blue region is basically allowed in the neutrino decay scenario. So we are not restricted to this 0.12 electron volt bound. And so the model mass prediction is in accordance with the cosmological mass bound for somewhat nice Majorana scales and Yukawa couplings. Okay, so and as an outlook and conclusion, basically, that we hope to have some data from Desi and Euclid in the near future of 5 to 10 years that will make this neutrino decay scenario testable. And thank you for your attention.
Thank you very much. The session, this is open for questions.
There's a question by Zeligio.
Okay, let's go.
Yes, I would like to ask, in your model, what happens to the number of effective neutrinos or relativistic species?
You mean the n-effective bound of
Yeah.
BBN and CB? Yeah. I mean, it gets increased, but we incorporate also the BBN n-effective bounds, and it's not enhanced, because I mean, you need also them to be thermalized around this time, and this will not happen in our model. So the n-effective bound is not relevant.
Okay, thank you.
Okay, other questions should be asked in the Slack channel. We're a little behind time. So let's thank the speaker once again. And we're going to go back to Beatrice and see whether she has solved the noise problem has been solved.
Can you hear me?
Yes, we do.
Okay, so it seems so. Okay, I start sharing the screen.
Yes, that's much, much better.
I don't know which was.
And we see the screen.
Now works, so. Okay, so sorry for the technical problem. I'm going to present the outer veto prototype we are developing in COA for the nucleus experiment. Nucleus is interested in the coherent elastic neutrino nucleus scattering, a process that, as Francesca said, was predicted in 1974 and observed for the first time just in 2017. This process is interesting because could be a new way to prove physics beyond the standard model. Assuming that the momentum transfer is sufficiently low, then the neutrino scatters off the target nucleons as a whole. The standalone signature we want to detect is a nuclear recoil characterized by really small energies, typically in range of tens eV to few tens keV. But on the other side, we have also a huge advantage represented by its cross-section. Since it is proportional to the square of a neutron's number of a target nucleus, then it is 10 to 1000 times greater compared to the standard neutrino detection channels. And this, as consequence, means a miniaturization of the detectors. Furthermore, we have no energy threshold in order to the process can occur. So, the nucleus experiment is developing some gram-scale cryogenic calorimeters using the CREST technology and based on cadmium, tungstate, and sapphire crystals, equipped with TESIs as highly sensitive sensors. The nucleus goal is to have an energy threshold below the 20 eV. Since this experiment will take place near the two nuclear reactors of the Shu nuclear power plant, a veto system is fundamental, and one of these of the elements of the veto system, is the outer veto. The outer veto will be composed of 6 high purity germanium crystals with electrodes in order to read the ionization signal. And as you can see on the figure on the right, this system of germanium will host the target detectors, and it will work in anti-coincidence with them. So, until today, we performed 2 tests for the nucleus outer veto prototype, and this test took place in IGC lab. In the first test, we used just 1 germanium crystal, while in the second test, we added a second germanium crystal with the same features of the first one. In this slide, I'm just summarizing some details about the 2 tests we performed. I want just to underline that in the first test, we used a cold electronics, while in the second test, we used a room temperature electronics, not optimized for ionization measurement. But in this second test, we had the help of a LED shield that was missing in the first test. So, here you can see a comparison between the 2 energy spectra obtained with the same germanium in the 2 different tests, and in the table some parameters are extracted from the measurements. I want to put in evidence that the first test, unfortunately, was not in the optimized cryogenic conditions. But these two tests were enough to understand that with our prototype, we are able to satisfy the nucleus requirements, even if is important, is fundamental, called electronics and a lead shield in order to reduce the pileup. For this reason, we perform also a third test, using the same detector using the second test, but testing it in the cryostat with the cold electronics. And this time we added a completely new lead shield and we optimized the cryogenic conditions. So the data analysis is still ongoing, but I can say that the preliminary results are really promising. Last thing, and I finished. This prototype will be sent in Munich in order to test the nucleus electronics, since now we know perfectly the properties of this detector. So thank you for your attention.
Thank you very much, Beatrice. And the audio was fantastic. So we have time for one quick question. Okay, no questions.
Okay, I'm available on Slack anyway. So.
Okay, in the Slack channel. Thank you very much.
Thank you.
And thank Enrique for helping solve the audio problem. Okay, so that is the end of the PhD forum, and I thank all 5 of you for wonderful talks, and they were excellent. I learned many things. So let's move on to the next speaker, which is Ian Schumacher, who is going to tell us about how to discover beyond the standard model physics in neutrino experiments.
Hello, everyone. So let's see.
Yep, we hear and see you and see your slides.
All right, great. Well, thanks so much for the invitation, and thanks very much to the organizers for putting together a very exciting program. It's been great listening to all the talks so far. So I think we all agree we need to find new physics, and we know that there's new physics out there, there's no doubt. We know not only because there's dark matter, not only because neutrinos have mass and baryons have an asymmetry we don't understand. We know all these reasons that there has to be new physics beyond the standard model, but we're otherwise pretty ignorant about where that new physics is hiding. It could be at energy scales just beyond our reach, for which we're going to discover in future high energy colliders, or it could be that whatever the new physics is sort of hiding beneath our noses at existing, accessible energy scales, but just at very small couplings. So we just need to have higher intensity experiments to go and probe models of that type. And I think, we really need this sort of multi-pronged effort to go and find new physics, because we don't have good clues right now about which direction is more promising. So we should explore all avenues to accelerate the search for new physics. So I'll mostly be focused on this latter category in this talk. I'm using the intensity frontier to probe new physics. So the general class of experiments that I'll be talking about has the following features so neutrino experiments, where what we're doing is sending in a beam of protons onto some target, producing neutrinos. And ordinarily, the following steps occur, right? We have proton collisions creating some batch of unstable mesons. They give us things like neutrinos. Neutrinos undergo some known propagation. Either this detector is very nearby to the target, and then there's basically no neutrino oscillations, or it's far away and it undergoes, the oscillations I know how to describe with the 3-flavor neutrino framework. And then the neutrinos scatter in the detector via known, electroweak processes. But if I go to a beyond standard model case, all of these steps can be modified in interesting ways. So one important one is that right away in the first step in the collision, I can directly produce potentially some new particles, or I could potentially use the decay of the mesons to give me some new particles. And so roughly speaking, I have two possibilities for these particles that I'm creating in the collision. Is they could be unstable. So perhaps I get some flux of some unstable particles that decay in my detector. So things like dark photons, heavy right-handed neutrinos, which we'll talk a little bit about, can do these things. I could also have stable beyond standard model particles, new particles that come in, deposit some energy via scattering. So examples of that category are things like light dark matter and milli-charged particles. Another process can be modified. So I could, for example, say all of the first three steps are fine. I produce just ordinary neutrinos, but now the neutrinos, when they enter, they do something new. They may scatter via some new process that we can't explain in the standard model. So categories of BSM physics that can do things like this include non-standard neutrino interactions, or what's usually called NSI, the so-called dipole portal interaction, which I'll talk a little bit about, and then Z primes. So if I have some new gauge boson that neutrinos couple to, I can do things like modify scattering rates or do more exotic things like produce trident signals, which I wouldn't expect otherwise. And then the final category, which I won't say anything about in this talk, but just to highlight it, another very interesting possibility that's been very well explored is that neutrinos can also undergo non-trivial propagation. And one simple way this can happen is from having new states occur, new, for example, sterile neutrinos that modify oscillation probabilities. So the rest of the talk's divided into two chunks. So I'll talk a little bit about the types of neutrino beyond standard model physics first that you can search for at neutrino experiments. And then in the end, I'll say a little bit about the searches you can do at neutrino experiments for things that have nothing to do with neutrinos. So to roughly bracket sort of the space of possibilities, let me divide up new physics into two perpendicular directions. So sitting down in the left-hand corner is the standard model where we have known forces, known neutrinos. So I can imagine extending this in two ways. One, I just add some new neutrinos, and these are by convention called sterile neutrinos because I'm just adding gauge singlets. I don't do anything to modify their interactions. They just come along and mass mix with the ordinary neutrinos. I can do another distinct class of new physics, which is I modify the interactions of neutrinos. This could come about from adding some new vectors or scalars, or just putting in by hand some contact interactions to modify neutrino interactions. And in principle, I could even imagine something in between these two extremes where my new neutrinos aren't really sterile, but have some new interactions. So a good example might be gauging B minus L, for example. So I automatically, for anomaly cancellation, have to have 3 additional neutrinos for B minus L, and they automatically couple to a new force carrier. So these really wouldn't be sterile neutrinos, even though sometimes we may call them that. So first, let's just talk about this category where I just add truly gauge singlet fermions, or otherwise called sterile neutrinos. So unfortunately, I don't have good theoretical arguments for how many there should be. There's no good arguments that I can borrow from the standard model where I get to use anomaly cancellation to tell me how many charged fermions I have around. Since these are gauge singlets, they're not bound by arguments like that. So I don't even know if it's 1, 2, or 17 sterile neutrinos that are around. I know I need to have at least 2 for explaining the atmospheric and solar mass splittings. And if there's a third one, I can even explain dark matter. There's a variety of ways of constraining these states because we don't know the scales we don't know their masses. So as I mentioned earlier, right, we could use modified oscillations. Some other possibilities which have been a little less explored are using upscattering production and also meson decay production. I'll say a little bit now about the upscattering possibility. So although these are sterile, because they have mass mixing, in a sense, they inherit a suppressed piece of the standard model weak interaction. So I can take processes like this neutral current diagram on the left, where I just have neutrino come in and exchange a Z boson with a fermion. This allows for the following phenomenologically interesting possibility that I can use some of E equals mc squared. I can use some kinetic energy for an incoming neutrino to convert into new mass, into a new heavy particle, this heavy sterile neutrino. And it does so with a cross-section, which I can just get from a standard model cross-section times this, this mixing angle. So we looked at this possibility in the following context at the IceCube experiment using atmospheric neutrinos. So as you may know, IceCube is a very large detector in Antarctica, roughly 1 cubic kilometer, very large, but not to scale here. It's not quite that large. And we were looking for we used a naturally occurring flux, the atmospheric flux, which comes from cosmic rays bombarding the Earth's atmosphere, producing a number of things, but at the end of the day, giving us neutrinos with a well-characterized flux. And this process allows for the possibility that upscattering occurs in the detector, in the IceCube. So the very high energies of atmospheric neutrinos can give me a way of producing sterile neutrinos in the detector, inside IceCube's volume. And this leads to an interesting distinctive signature, which is in the first step, which we just discussed. So the neutrino comes in, the active neutrino comes in and scatters into this heavy state. What I see in the detector, because these are very high energies, I basically see, you know, some large energy deposition from the scattering on the neutrons or protons. So let me call this bang number 1, which I can see visibly inside IceCube. This produces distinctive Cherenkov light. But I've really produced this state now, and it can travel macroscopic distances before decaying. And this travel time is fairly short. It's moving very close to the speed of light. So it travels some macroscopic distance and decays again. And oftentimes, at least, not always, because we have to, you know, include all possible decay channels for this state, which we could get from just utilizing the fact that it has inherited a bit of the weak interaction. So all of its decay modes are basically just dictated by kinematics plus the standard model interaction it inherits. And as long as it's decaying to something visible, so not just decaying to invisible things like all neutrinos, as long as it's decaying to some visible states I can see, then I get, in close succession from the first energy deposition, I get a second one. So we called this a double bang search, which has very low background that IceCube could go and search for. And especially in the case of looking at tau mixing. So here I'm plotting on the vertical axis the mixing angle between heavy neutrinos and the tau neutrinos as a function of the unknown neutrino mass, the heavy neutral lepton mass, showing existing bounds coming from Charm and Delphi. And along with what IceCube could do at the time, this was just using 7 years of existing atmospheric data. IceCube could go and fill in this open parameter space between the Charm and Delphi bounds without doing any extra work. So this is just using existing data. There is a similar signal that produces double bangs, but this only happens at much, much higher energies in the standard model. So worst case scenario, IceCube can produce new GeV scale sterile neutrino bounds. And best case scenario, they could go and, you know, discover sterile neutrinos in this way without doing any modifications to their detector or anything. So let me, since we're on the topic of heavy neutrinos, let me say a little bit about what happens if these heavy neutrinos have additional new interactions. And first, let me justify that a little bit. So it may seem odd to imagine this slightly Baroque scenario where we have, you know, multiple ingredients all at once, right? Not just a sterile neutrino, but also some new interaction. And on the one hand, although we like simplicity, we like using things like Occam's razor, nature doesn't always seem to abide by Occam's razor. And dark matter may suggest that there's, you know, some whole new zoo, some whole new sector of particles and forces. So if the nature of beyond standard model physics is like that, then it's worthwhile to consider the possibility that sterile neutrinos come with extra interactions. And this can do a number of interesting things along the way. It can, you know, incite new strategies for experiments, can help us look at existing data in a new way. And it also will, shuffle around existing experimental sensitivities. So it will, basically give us a new way of seeing how all the experiments fit in together and who has, the best sensitivity at what mass and so on. So one scenario I'll discuss in this context is what's called this dipole portal. So this is with this Lagrangian. So the ordinary left-handed neutrinos couple now to this heavy, I could call it a sterile neutrino, but a heavy fourth neutrino, and also couple to the photon. So you can think of this as a transition dipole moment. So this paper from 2018 did a very nice job looking at sensitivity to such an interaction at SHIP, at the early universe, and at supernovae. And one nice thing is that, you could see in this plot where we're plotting on the vertical axis the strength of the dipole interaction as a function of the unknown sterile neutrino mass. You can see that, at the low coupling end, supernovae do a very nice job, better than any terrestrial experiments, but at the higher coupling end, terrestrial experiments come in and fill in the parameter space, but there's still an interesting gap. And I also just want to highlight these papers at the bottom, two of which at least were motivated by the xenon 1-ton excess, and then this other very interesting paper by Plested looking at upscattering that can occur in the Earth and then allow for the heavy state to decay in your detector. So we looked recently, actually there are a pair of papers recently looking at Dune's sensitivity to this type of interaction. So on the left-hand side, we just did sort of the same thing we were doing for IceCube, which is go and look for this double bang signature at Dune. And the reason for this sort of funny shape in the sensitivity, this sort of wedge shape in the sensitivity, comes from the fact that I'm asking for two things in the signal. I'm asking for, bang number 1 and bang number 2. And the finite size of the detector basically sets this lower boundary. There's a maximum separation I can allow for me to see two distinctive signals. At the same time, I also need to have a detector with fairly good spatial resolution so that I can really see that I do have two well-separated bangs. So if I had finer and finer spatial resolution, this upper boundary would move upward and I would have better sensitivity. So it's a non-trivial fact that Dune has the ability to probe such a signal. It's a big enough experiment that simultaneously has good enough spatial resolution to look for this and can eat into new parameter space. And a complementary, very distinctive signal that this paper also that came out this year looked at, that we heard about earlier today, was using the FAR detector to go and look for monophoton signals. So this heavy neutrino comes in to the detector after undergoing upscattering en route to the FAR detector, and then decays in a distinctive monophoton signal. So it's not about looking for these new states in just one way. It's great that we have a number of phenomenological signals to look for. And in principle, we can look for all of them. So as I wrap up this section about new beyond standard model neutrino physics, let me say a little bit about non-standard neutrino interactions. So this portion of the BSM schema diagram, I don't have any sterile neutrinos per se in this direction. I just have some new interactions. So these are very well explored. This idea goes back at least to the seminal paper by Lincoln Wolfenstein, which first observed the existence of this matter effect. So one important way that one can search for what I'll call NSI, which is where I just have, say, a new contact interaction between neutrinos and some charged fermions. One important way, which was also pointed out in that Wolfenstein paper originally, is I can use oscillation data, because this will modify the matter effect. So as long as neutrinos are propagating in medium, their oscillation probabilities will be modified by new physics contributions like this. And there's been a huge number of papers exploring this possibility. A very interesting direction, which I think has recently picked up steam, mostly because of Coherent, is using scattering data. And then a final distinctive possibility is to use collider data, right? So you can also, have the diagram now with time flowing upward. I can potentially use charged fermions at a collider to produce anomalous missing energy signals. And this possibility has been explored in a number of papers as well. All of these are very incomplete lists. So if you're interested in NSI phenomenology, I highly recommend this review by Farzan and Tortola, or the status report that came out in 2019. These are very, very incomplete lists of NSI phenomenology. So as I mentioned, so coherent elastic neutrino nucleus scattering is a very nice distinctive probe of NSI. This was already mentioned a bit in Francesca's talk earlier today. And just to remind us about coherent, right? So the idea is these are very low energy neutrinos coming in and scattering on all of the nucleons in the nucleus in a coherent way. And this was finally observed in 2017, and being consistent with standard model expectations can be used to constrain BSM contributions to neutrino scattering. So just as one example of why this is interesting and relevant is because of a very interesting oscillation scattering complementarity. So if I'm restricted to only having access to oscillation data, we actually don't know what certain values of the vacuum oscillation parameters are. So in the standard 3-flavor framework where I don't have NSI, we believe that theta 1, 2 is around 34 degrees. If I allow for non-zero NSI, which I'll just parameterize in terms of some dimensionless parameter epsilon in units of the Fermi coupling, if I allow for that, I can have theta 1, 2 be a very, very different number as long as this NSI coefficient is rather large. And oscillation data is insufficient to tell me which is correct. Coherent can come in though, right? We're not operating in an experimental vacuum. We have other data around besides oscillation data. And coherent data, it was pointed out, can exclude this so-called LMA dark possibility, the possibility that theta 1, 2 is over here. So this holds at least in the limit that NSI is well described by a contact interaction. So it's been pointed out that if you violate that assumption, if NSI is not described by a contact interaction, but instead comes about from some relatively light scale Z prime, which I'm plotting here, it's coupling to neutrinos and nuclei along with the unknown Z prime mass. So the black line is showing where LMA dark lives. And you could see that at high masses, the current coherent data in blue would exclude your ability to lie up there where LMA dark is. But if you go down to lower masses, the coherent bounds end up becoming somewhat weak compared to where LMA dark would like to live. And you can get away with potentially having sizable impact on the matter potential, so potentially allowing for this LMA dark solution while being consistent with coherent data. This could be tested with future sevens data, and I just want to also highlight two other very interesting works about accommodating LMA dark in light of coherent data. So in what remains, let me say just a little bit about what you could think of as sort of happy accidents. So going and using neutrino experiments to do things very different than what they're intended to do, look for things that have nothing to do with neutrinos at all. So one such possibility is in what's called secluded dark matter scenarios. So this could be a scenario where dark matter has no direct gauge interactions, and yet, depending on the nature of the dark sector, may have one of three renormalizable portal interactions that I cannot forbid by gauge invariance or Lorentz invariance arguments. The most important of which in this context is the photon portal. So in this scenario, there's an unknown coupling epsilon that allows for kinetic mixing between our photon and a new dark photon. So because of this kinetic mixing, neutrino experiments, which have an abundance of mesons produced in the collision, right, the protons being dumped on a target, I get tons of pions and etas, which ordinarily do things like decay to 2 photons, but now, in view of this kinetic mixing parameter, can produce an on-shell dark photon, which decays to dark matter. And then, so I basically have a flux, a beam of dark matter coming in, which can scatter and leave energy deposition in my detector. So a number of papers have looked at this, exploiting either, on the one hand, the ability of the Dune prism near detector. So this is the ability of a component of the near detector to move off axis by up to 35 meters, which allows you to suppress, which allows you to enhance signal to background ratio. And then on the other hand, exploiting the very good energy resolution Dune will have that will potentially allow you to do a very good spectral analysis, basically a shape analysis, to disentangle the energy deposition you get from something like this compared to what you get from neutrino electron elastic scattering, allowing you to test even very well-motivated parameter space. So I'm plotting, so here, sorry, the authors, not me, but the authors of this are also plotting this dashed blue curve, which is the parameter strength you need to get the correct relic density for dark matter. And so you can see this red curve, which is the most optimistic case, this on-axis configuration will allow you to probe the relic density hypothesis for this class of dark matter models. So the very last piece of non-neutrino physics I'll just highlight that you can do at neutrino experiments is to go and look for axion-like particles. So an axion, hypothetical axion-like particle may couple to FF dual in the following way, allowing for any of the photons you produce in the collision process from your protons hitting your target to, via Primakov production, produce a flux of axions. And the flux of axions can either scatter or decay in your detector. And we found recently very nice complementarity between scattering on the one hand, which allows, for which the liquid argon component of the near detector is very helpful with its larger density. Scattering is the way to go with the liquid argon detector. But in the piece of parameter space where decay dominates, you just basically want the biggest net possible to capture all of those decaying particles. And in that case, the gas phase detector does the best job. And you can already see with this very sort of rough analysis of looking at what Dune can do at the near detector, that Dune should be able to eat into this so-called cosmological triangle, where only so far cosmological arguments have been able to probe, and also eat into this sort of tan region where we've only been able to probe using astrophysics, things like horizontal branch stars or supernovae. So let me just conclude and take any questions. I think, to me, the upshot is that the BSM landscape is quite vast, and I think we still have many new elements of it to discover. And it makes sense right now, with all of the developments going on in the neutrino community, to cast a very wide net. So we don't know where new physics is lying. And doing this, I think, helps expand not just the theoretical terrain, but also widen experimental search strategies, which I think we need if we're ever going to find the new standard model. Thanks.
Right. We have time for one question. So anybody has a question, get your hand up ASAP.
Sandhya raised her heart.
Okay.
Oh, sorry, was there a question?
Hi.
Was
that you, Enrique?
Or not, I don't know, but you showed, can you go to the slide where you were showing the constraints using that double bang signature at IceCube for heavy sterile neutrinos?
Sure. Oh yeah.
Yeah, you went past it. So this is very intriguing. I mean, you have a constraint from deep core, and then you have a constraint from ice cube. But I presume the energy range of deep core would be different from the energy range of ice cube. So my question is twofold. What exactly determines that the sensitivity will come at 1 GeV? And why is it not different for deep core and ice cube? Does the energy of the neutrino does not play a role in this?
It doesn't play a leading role. Yeah, so it's right. So, I mean, the big difference with deep core is the smaller volume, but also, right, the lower energy threshold that deep core offers. So both of those are taken into account in this analysis, but at the end of the day, the bigger volume of the full ice cube detector played the biggest role in setting the sensitivity throughout the whole mass range.
So essentially, it is the mixing between the heavy and the light neutrino which is playing the dominant role.
Right, right. And also I want to emphasize too that so at the low, so it's slightly less apparent here, but you could sort of, let me take, say, one mass over here, right? So there's sort of two mixing angles that are crucial, actually at all masses, but it's especially apparent at the high mass here. So the physics that's playing the role in setting the lower boundary is the size of the detector. So bigger is better. If I imagined a hypothetical detector that was X amount bigger than ice cube, this region would go down without this curve doing anything. If I want to access more parameter space upward, the way to do that is to have better spatial resolution. So if I have better, and that's essentially set by the string spacing inside the detector. So deep core should actually do a bit better there.
Can you wrap this up, please?
Sorry?
I think, due to the time limit, I think you
Sure.
should continue this discussion on the Slack channel.
Sure.
We are a little bit over time here. So let's thank Ian once more. And then we're going to change gears. Let me see if I get this to work. Yes, so we're changing gears here, and we're going to talk, our next event is colors and flavors. And this is not talking about quarks, gluons, or leptons. This event was put together by Stefano Rigolin and Massimo Macero from INF Padua, and they have arranged for us to have a world-class sommelier to lead this wine tasting. This is Michael Leonard Flanagan. Although he has a Gaelic name, family name, he has lived in the Veneto region of northern Italy for the last 40 years. Michael is a board member of ISIS, the Italian Sommelier Association, which he will give us the official name, I'm sure, which has 40,000 active members. And Michael is actively involved in the education of new sommeliers in the art, the passion, and the language of wine. Please welcome Michael Flanagan.
Thank you very much. I was shocked, of course, about the invitation. I hope everybody can hear me. Even because I got frightened when I joined the screen over here, because my seminar is not going to be, of course, using the terms that you are using currently in your life. I'm trying to putting, of course, the screen presentation on the screen. And of course, this is not going to happen right now because we are live, and let's see if we can do it. Maybe we got something.
Yes, we can see something.
I don't know if you can see you can see my screen right now?
Yep.
Is it available?
Yes,
fine,
I can.
fantastic.
Yes.
So thank you very much for the invitation. I feel honored for the invitation. And when I spoke about this webinar meeting with one of your Italian colleagues, I said up front that my approach to colors and flavors will be the ones define my being sommelier. That is, of course, our systematic approach to wine tasting. Some of the scientific and the physics elements that are part of your daily faculty life, sorry, will not be elaborated today. We're going to be a bit more empirical. It's going to be a toast, a cheer more than all, elaborated in the background. If you belong to a different time zone, you can use this as an excuse. And it's probably too early to approach an alcoholic drink. I must reassure you that bottles or other drinking devices cannot read the time. So you are officially excused. And you are doing this, of course, for better and deeper knowledge. So I hope you enjoy very much this approach. And I'm giving you, of course, what is considered a very basic sommelier overall lesson. Excuse me, of course, where I will be faulty in some terms or definitions that are going to be strongly against, of course, the latest